Hi, this is Kevin Trainer, and I'd like to welcome you to my lecture on Chapter 4 of Murach's MySQL textbook. Chapter 4 is called How to Retrieve Data from Two or More Tables. I'm going to leave the objectives for you to look at on your own and get right into the material. So in Chapter 3, we learned how to code the select statement for a single table. And whereas that's a nice skill to have, it's the nature of relational databases that we split up the data in a pretty atomic sense, right? In our database design, what we try to do is we try to identify all the data entities in the problem space, and we try to create a table for each of them. And so, for instance, we would have a table for vendors and a table for invoices. So if we wanted a report like we see here on slide 4 that included invoice number and vendor name, we would need to include the invoice number from the invoices table and the vendor name from the vendors table, which means we need two tables. There's an occasional time that we want an answer that can be had from a single table, but it's not common. All right. So this skill that we're learning in the chapter is pretty basic to our success. And we're using a technique that we call join. Okay, so we are joining two tables, and if you look at the top of the slide here, you can see that the select list, that's standard stuff from table 1. We've done that before. Now we get into parts of the syntax for select that we haven't seen before. We can say join table 2 on join condition 1. And then we can keep on going. We can say join table 3 on join condition 2. So not only can we join two tables, but we can join 3 tables and 4 tables and 5 tables and, well, probably any practical number of tables that we would like to do. That sounds pretty complex, but actually tables are joined one at a time. Okay. And I'm sorry, 2 at a time. So if we are joining tables A, B, and C, the server will join typically tables A and B and take that result and join it with table C. So the rules for joining kind of only relate to 2 tables at a time, and that makes them pretty easy to understand. Here's an example of a pretty easy join down here on the bottom. Select invoice number vendor name from vendors, inner join invoices on vendors.vendor_id equals invoices.vendor_id, order by invoice number. Now, a lot of things to point out here. First of all, I can't overemphasize the order by. In a select, typical select, if you don't have an order by, you don't have a reliable order. So you always ought to be thinking of including an order by. Okay? From vendors join invoices, that makes sense because we want to pull from those 2 tables. What do we mean inner? Well, we're going to find out in a number of slides that there are outer joins, which don't work like inner joins. And so an inner join is a basic join. And the word inner is the default. So I'm never going to have you code inner. I would have you code from vendors join invoices. Okay? So inner is just a common garden join. Okay? And what's the on? Well, that's the field That's the column that we use to match the rows in the two tables. Okay, so both tables have a vendor ID column. Okay, and it turns out that the invoices table is essentially pointing at the vendors table, and so that we know from this that there's a relationship between invoices and vendors, and we're exploiting that in order to match up the rows. So when you look at the answer set, we only see a subset of the rows there. It matched all 114 rows in the invoices table. And as I recall, that's all we have there. Okay. And it's taking the invoice number from the invoices table and the vendor name from the vendors table. And we're getting a typical result. Now, I just want to point out that we got a match on every row, okay? Every row on invoices. So we have 114 rows on invoices. We have more vendors than that, okay? So we're not seeing the rows in the vendor table that don't have an invoice. Likewise, if we had a row in the invoices table that did not successfully point to a row in the vendor table, for instance, if you went to if you went to vendor ID and it had a null in it, then we wouldn't have gotten that row. Now, we probably set up the rules for the database such that we have a relationship between the two tables, and you probably aren't able to add a row to invoices unless it properly points to a row in vendors. So that's the reason why we got all the invoices that we expected. So things are working just as planned. Okay, now in the join that we just saw, we didn't use the table alias feature. So if we just back up, you'll see that when we referred to, for instance, on the on clause, when we wanted to differentiate between the two vendor ID fields, we had to put the full name of the table. We had to prepend it with a dot. So vendors.vendor ID, invoices.vendor ID. Table aliases are mostly a convention to make it easier to code those on expressions. Okay, so if we go here back to slide 5, you can see that we can use a short, typically table aliases are 2 characters long. We can use them once we alias the table. So we took table 1 and we gave it the alias A1. From there on in, we can use the name table 1 or A1 to refer to the table. And that just, it leads to a lot less typing. It leads to less cluttered code. It's both a convenience and a quality improvement if you use it well. Here is a join, an inner join, and I can't emphasize enough what's the difference between an inner join and an outer join. An inner join is a plain old join, and an outer join is something we're going to learn about in a bit. Okay, so we're doing select invoice number, vendor name, invoice due date, invoice total minus payment total minus credit total as balance due. From vendors, give it the alias V, join invoices, give it the alias I. Oh, I'm sorry, this is not, this is actually just using aliases for all the tables. I misread. In the on, we can say v.vendor ID equals i.vendor ID. And, a 1 or 2 character table alias makes the code read well and it makes it easier to type. Okay? Note that we do have an order by on here as well. Very good practice. Here's an inner join with an alias for only one table. Okay? So we have from invoices, join invoice line items. And I guess we thought that whereas invoices is a short name all by itself, invoice line items is too long. So we gave it a line items alias. And then, of course, in the on clause, we can use the line items alias in the code. So just because you use an alias for the name of one table doesn't mean that you have to use it for all the tables. It's a convenience. Here's some syntax where we are not only showing the name of the table, but we're prepending the name of the database. And this is because we can join tables from one database to another database, provided that we've planned ahead and they're in the same database server space. Okay, so here we are. We're selecting the field some vendors with an alias of V. Join OM. That's another database. We are in AP right now. So join the customers table from the OM database and call that C. And then we can use the V alias and the C alias in the on clause. Okay, so it's possible to join tables from more than one database. So here are here's just a look at some of the data in the sample database. Again, this is the AP database. Oh, no, it's not the AP database because it has customers and employees. So it must be the OM database, order management. So in customers, we see we have customer ID, last name, first name, address, city, state, and then some more things. In the employees, we have employee ID, last name, first name, department number, manager ID. Now, I want to point out that these department number and manager IDs are foreign keys. Okay, they point to rows in other tables. Manager ID probably points right back to the employees table. Department number is going to point to a row in the departments table. Here's an inner join with two conditions. Okay. So we're saying that we want to get customer first name, customer last name. We want to join customers with employees, give them each an alias, and then we want the first names to be equal and the last names to be equal. So in order for us to get a row in the answer set, both of those have to be equal. If either of those is unequal, then that row from that table is not going to be included. We're looking for a match, a complete match. Okay? In this case, we're trying to figure out how many customers are also employees, or even better yet, how many employees are also customers. And hopefully we think that's a good thing. We want the employees to patronize our business. Now, here's one of the tricky uses of alias. Okay? It's possible to join a table to itself. Now, on its face, that seems a little redundant, and it is. But what we want to do is we want to have a relationship between, say, in this case, so what are we trying to do? We're working with vendors, right? And we're trying to find, so we want to list the vendor name, the vendor city, the vendor state. And we're going to join two copies of vendor. And notice whereas we use the same table name, we use different aliases. So when we're using the V1 alias, we're referring to, you can think of it as copy 1 of the table. And when we use the V2, you can think of it as copy 2 of the table. So you can really think of there being 2 copies of the table and that we're going to join them. So we're going to say on the cities being equal, the states being equal, and the vendor name not being equal. Okay, so what we want to do is we want to find the ones that are not duplicates. Okay. So one of the problems that you have when you self-join a table is that rows tend to match themselves. And of course, that's why we've got the vendor name. So what we're trying to do is we're trying to find how many city-state combinations have more than one vendor. And so we can see in Phoenix, we've got 3. In Anaheim, we've got 2. In Fresno, we've got 3. Okay. So this takes some getting used to. It's a little razzle-dazzle, but it's one of the fun things that we can do with relational databases. Here's a slide that joins 4 tables. I apologize that I jumped the gun on claiming that a little bit earlier. So let's see. We are selecting vendor name, invoice number, invoice date, line item amount, account description from vendors, and then we're joining invoices, then we're joining invoice line, then we're joining general ledger account. Okay. So let's see. How are we joining vendors and invoices? Well, on vendor ID. So they both have a vendor ID column. How are we joining invoices to invoice line? On invoice ID. They both have invoice ID. How are we joining general ledger to invoice line item? On account number. They both have that. Okay, so we've got a link. We've got 3 links that connect 4 tables. Vendor ID is link 1, invoice ID is link 2, account number is link 3, and you need 3 links to connect 4 tables. And then the other thing to remember is the rows that we're going to get in the answer set are only the ones that match all the way across. Okay? And interestingly, we only get 11 rows. Now, the syntax that I showed you for the join, where we use the join clause, is relatively new. And what I mean by relatively new? Well, I believe it came from SQL 92. So way back when I learned SQL the first time, which was in the 70s, we didn't have a join. So how did we make a join happen? Well, the join keyword is an explicit syntax that we can use for joining tables. And it's the preferred method, okay? There is an older approach that we see here on slide number 13. That is the implicit syntax for a plain old inner join. And what we do is we list the tables in the from clause. So you can see in the syntax diagram here, from table 1, comma, table 2, etc. And then the forcing the linking columns to be equal takes a place in a where clause. So we say where table 1 column name operator table 2 column name. So what does this look like when it's got real examples in it? Well, let's look at the bottom example here. Select invoice number, vendor name. We did this before. From vendors V, invoices I. So you can use the table alias name even if you're not using the explicit join syntax. Okay, where V vendor ID equals I vendor ID. Order by invoice number. Now this is the equivalent of the one that we did several slides ago. Which do I prefer? The one I taught you first. Okay, it's less error prone and it's more modern. So you can do it like this. I would prefer that you didn't. And let's see, could we join 4 tables using the implicit syntax? Sure, we could. So we just take the same example that we had before. We list the columns that we want to select, and then in the from we name 4 tables. We don't use the keyword join. We are creating aliases, and then we've got we have got 3 parts of the where clause are doing the linking of the tables. So the first 3 conditions of the where clause, vendor ID, invoice ID, account number, those are the ones that do the linking. The 4th one, invoice total minus payment total minus credit total greater than 0, that's a real typical where clause that we would use to limit the number of rows in the output. Okay? So again, which of these do I prefer? I prefer the one, I would like to see use the one with the explicit join syntax. Okay, let's talk about some terms to make sure that we understand those. A join is the combination of 2 or more tables in a single select. Join is also the keyword that we can code on the from clause to make that join happen. A join condition is the expression that identifies the columns that link the 2 tables. Now, it's typical that it's a single column, but it doesn't have to be. Sometimes we have some kind of a complex key that is made up of more than one column. But it's typically a single column, and they're typically equal. And if in fact they are the same data item, then they typically have the same name. Okay? Things like we're going to say, well, why don't we back up? We're going to be saying, we're going to be using things like on vendor ID equal vendor ID. Okay? We're going to be doing stuff like that. Okay? So those are join conditions, on conditions. An inner join, the only kind of join we've learned about, a plain old mom and pop common garden join. Okay? What about outer joins? We didn't get there yet. Ad hoc relationship. Okay. Now, I mentioned this before. Okay. Some of our tables have constraints on them that help the server maintain what we call referential integrity. So if, for instance, in our invoices table, we have a vendor number column, okay? If we set up a foreign key constraint, which we're going to learn how to do when we get to about chapter 10, then it's only going to allow us to insert a row into invoices if it's pointing to a proper row in vendors. So that's an explicit relationship, okay? We can try to exploit a relationship between two tables that is not governed by a foreign key constraint, in which case we're probably going to expect fewer matches. And when we try to do that in our code, that's sometimes referred to as an ad hoc relationship rather than the one that was designed in. What's a qualified column name? It's a column name with either the name of the table prepended to it or the name of the table alias prepended to it. What's a table alias? Usually a short character string expression that allows us to do two things. The most common thing is it allows us to type fewer characters when we want to refer to the columns in that table. The other thing it allows us to do is to self-join tables. That's two down from table alias. So it's possible to include a table more than once in a join and give it two aliases. And by and large, you can really think of there being two tables. One is the copy of the other. Does it copy over the table? No, it doesn't copy over the table. But you can think of it that way. And I find that helpful. I hope that you will too. A schema. A schema is a lot of things, but in MySQL, schemas are databases. So the AP database is the AP schema. A schema is a set of rules for defining the data in a particular database, right? So the names of databases and the names of schemas are interchangeable in MySQL. A self-join is when we join a table to itself. That can only be done with table aliases. Okay? Explicit syntax. So when we join two or more tables, it's preferable to use the join keyword and to join them explicitly in the from clause. Okay? That wasn't introduced until 92. That was introduced in the standard called SQL 92. Okay? In the bad old days, when Kevin learned SQL for the first time, we didn't have that. And so the matching up of the columns, which made the join happen, was done with the where clause. So the where clause was carrying really two loads. One was to constrain the table matching such that we made the relationships happen to link the table. So it was used to make the join happen implicitly. And then it was also used to further limit the rows in the answer set. I like the version where we used join explicitly, and then we're only using where to limit the rows in the answer set. I think that's a good division of labor. It's a good division of thought. And it turns out that the explicit join syntax is less error prone. So, the explicit syntax for an outer join. We've already been using it, all right? So we're seeing it here on slide number 16. So here we say select list from table 1, left or right join. We can say either outer or inner, although we're not showing inner there. And then right after we say what to join, then we express the on condition or conditions that are to be used to link the table. And then we can keep on going. Okay, what's an outer join? Well, remember, an inner join is just a plain old join, right? And an inner join, in order to get a row in the answer set, there has to be a match between the left and the right. Okay, so rows that only appear in the left table, they don't appear in the results set. Rows that only appear in the right table, they don't appear in the results set either. Only the rows that actually join across the condition, only those rows will appear in the answer set. Okay? That's typically what you want because, again, when we design our databases, okay, we often, if we have a relationship between two tables, we make the relationship explicit. We provide a constraint on the table that is pointing to, so on the one side pointing to the many, on the many side pointing to the one side. We'll get to that in a couple weeks. And we say that you can only add a row to invoices if you have a vendor ID included in that row that points to a row that exists in vendors. Okay? So then if those rules are true when you are building invoices, then you should always expect every row in invoices to match across to vendors. Okay? Shouldn't be a problem just on the basis of how you built the constraints into the databases. Okay? Now, there are times when there is a possibility of not matching. Okay? Let's... I'm trying to think of a good example of that right now. Here's one that I kind of like. Let's say that some customers are so important that they're assigned a dedicated salesperson. So there could be a relationship between a customer and employee such that we are pointing from the customer to the employee to say that's the special salesperson for this customer. We don't do it for all customers. Okay? So what's there for normal customers? Well, typically a null value. Okay? And when we create the constraints for the database, we are going to say that on customer, when you add a new row, you might have a pointer to the employee for their dedicated salesperson that might be null. Okay, or it might be populated. So then, when we go to list out the customers, what if we want to list out the customer and then the name of the salesperson if there's a dedicated salesperson? Well, that creates a either a problem or an opportunity that is solved by outer joins. How's that? Well, if we do a plain old join, a plain old mom and pop inner join, and we join the customer to the employee, and we're using that employee ID that is to point to the special rep for that customer. Um, if in fact we do a normal join, we're only going to get the rows and customers that have a special salesperson. So we'll get the name of the customer and the ID, whatever comes we ask for. And then we'll get the employee information for the employee who's that special salesperson. But we won't get any customers that have no special salesperson. Okay? But what if we wanted a list that included all the customers, and if they had a special salesperson, we wanted to show their information. If they didn't, we wanted to show a null. This is what you do with an outer join. Okay? So, you retrieve unmatched rows from one table or the other. So a left outer join will retrieve unmatched rows from the left table. A right outer join will retrieve unmatched rows from the right table. Okay? Now this is just the situation that you want where you're expecting some things to be matched and some things not to be matched, and it's the nature of the rules of your application that you want that. For instance, this having the property of being assigned a special salesperson, it doesn't happen to everybody. It only happens to some. Okay? So here's a left outer join. Okay? In this case, we're looking for vendors and invoices. Okay? So we're saying that we want the vendor name, invoice number, invoice total from vendors left join invoices, where vendor ID equals invoices vendor ID. So what's this going to do? Well, this is going to take the left table, which, as you can see, is vendors, and it's going to retrieve the rows in vendors, whether they successfully match across to invoices or not. Okay? So here we're listing out Abbey Office Furnishings has one invoice. American Booksellers doesn't have any invoices. Well, how do we know? Well, we get the column, we get the vendor name, but then in invoice number and invoice total, we get a null. Okay? I just want to point out, if we had the same vendor had 3 invoices here, we would have gotten 3 lines for them. So if we have no invoices, we get 1 line, but we don't see any information for the invoice number and the invoice total because there's nothing to match to. Now, if we did a plain old join, we wouldn't have gotten those lines that have the nulls. Okay? How do we know we want it to be a left join and not a right join? Well, because what we're trying to do is list all the vendors in the invoices that apply. If we did a right join, we would list all the invoices and the vendors that apply. Okay? Because of the rules we set up when we created the database, we probably don't even need to do that, because every invoice probably has a vendor because of the constraints we put on the database. Now, I just want to point out that we don't say left outer join. Okay? And that is because outer is implied. Okay? So as soon as you say left, it knows you want an outer join. As soon as you say right, it knows you want an outer join. There's no use for left or right keywords other than to create outer joins. So they could have said left outer join, but they just said left join. So here we've got some more tables. We have a departments table. We have, and this is the classic situation here. I love these examples. So we've got 5 departments, counting payroll, operations, personnel, and maintenance. And we've got 9 employees, okay? And when you look at the employee table, there's a department number, okay? That's a foreign key that points to departments table. And you can see that they're all populated, right? There are no nulls. The next column, though, manager ID, well, what does that point to? Well, that's a self-join, okay? That's a relationship back to the employees table. Even though manager ID and employee ID don't have the same column name, because they can't, because they're in the same table, they do represent the same data concept, okay? Now, in most organizations, there's a person who's not going to have a manager, right? They're the super manager, they're the chairman, they're the president, they're the CEO. So we see for Cindy Smith that she doesn't have a manager ID. So what does she have there? She has a null, okay? So for instance, if we were trying to list out the employees and their managers, if we didn't do an outer join, we wouldn't get Cindy Smith because she doesn't have a match on the manager ID, okay? The only way to get her to come out in the answer set is to do an outer join. So let's see what we do. Oh, now we have a projects table. So here are a bunch of projects and the employee IDs. Okay, so this is a project assignments table, okay, where we have a project number and an employee ID. So I think what we're really looking at here is a relationship that's going to be a many to many. So this is a so-called associative table that connects the projects table to the employees table. So we can see for P1011 we've got 2 employees on it. For 1012 we've got 1, 2, 3 on it. For 1013 we've got 2 on it. For 1014 we've got 1 on it. Okay, so that's how you read that table. So here we're doing a left outer join, okay? So this is a classic case where either because we're expecting this, or because, I'm sorry, expecting this is a bad expression. There are times when you have all the data properly populated into your system, you're not going to expect to have a department with no manager, right? Because here we've got a department name, a department number, and a last name. I think that's the name of the manager. Okay, so what we're looking for is, do we have a department in which we haven't populated it with the manager name? So this is almost like quality assurance kind of a query. So we left join employees, so we're going to get everything from employees. I'm sorry, we have departments left join employees, so we get all departments and we get the employees that match. Okay, and then we're doing last name, which is coming from employees. So we've got accounting 1 Hernandez. We've got operations 3 null. And I'm having a little bit of a hard time kind of figuring out what we've got because we've, oh, that's just a department number. Okay, okay. So, apologize for this. Um, Sometimes the sense of these queries evades me. Okay, so this isn't a manager situation. This is only the employees and their departments. So we can have each of the departments is going to employ, each row represents the combination of a department and an employee, except for operations, where it represents a department and no employees. So the first two, we've got 1 employee per department. Operations, we have department 3 with no employees, so that's why we get the null. Then we've got 3 employees that are part of the payroll department, and then 2 employees that are part of the personnel department. So again, we got all the departments, even operations, which hasn't been assigned any employees yet. Now that might be because we have not fully populated the data. Okay, so this could be the kind of query that we do to make sure that we've got the data properly populated into the database. Or it could be a common occurrence that happens within the business, and we just, we want to be able to see that we don't have anybody currently in the operations department. Maybe some parts of the company have people in operations and some don't. I don't know. Now here's a right outer join. So again, we're doing departments on the left, employees on the right, but we're saying right join. And again, as soon as you say right, you mean right outer. Okay, right outer join employees. So we should be getting all employees. Okay, and then we should be seeing and then we should be seeing the department if they have one. So for the first two, Watson and Locario, the department name is null because it was not on the non-failing side of the join. Okay, so we're going to get the employees whether they match or not. And then all the rest of the employees match. So we can see we've got 3 to payroll, 2 to personnel, 1 each to accounting and maintenance. And then we've got 2 people who are currently not assigned a department. Now this is interesting because they say they're part of Department 6, but there isn't a Department 6 in the department table. So to me, that's sort of a data integrity problem. Okay? If we had a null in department number, which is to say that, well, we haven't told the system which department they're part of, that's fine. But I don't like the fact that we have a 6 in each of the department number fields and then we have a null in the department name. That means that we have a relationship between the employee and the department where we haven't maintained referential integrity. Probably because we didn't properly set up a constraint for a foreign key. So this is bad data integrity and boo hiss. We don't like it. Join 3 tables using left outer joins. Okay, so how are we doing this? Well, we have departments, left join employees, left join projects. Okay. Now when we do this, all right, every time we join, we get a result set. All right. So what we're saying is that absolutely we're going to get all of the employees. Okay. Plus, I'm sorry, we're going to get all of the departments. That's the first one. And then, so that's why we have a list that includes all the departments, even operations. It doesn't have any people. Okay. And then we're saying of all of the departments that have people, then we want a list of their projects. Okay. And again, if they don't have any project, we'll see on null. So the way a query like this works, if you take the line in operations where in last name you have a null, there's no way to have a project number over in the right side because we've already failed. Okay. Whereas here down in personnel, we've got personnel Jones. So we succeeded in having a connection between department and employee, but then there's no connection between the employee and a project. Okay, so if you get a null in the middle column here, then you have to have one in the right column. If you get data in the middle column, then you may or may not have data in the right column. And this is a case where they were all outer joins. Okay. Combine an inner and an outer join. So we have departments join employees. So we're only going to get the match. Left join projects. Very good. So do we have all the departments? No, we didn't get operations because that has no match to employees. Okay. So again, this first join is just a normal join. It's not a left outer join. Okay. Okay. And then from here, so we do have all the employees. Okay. And then we only matched, and because we had an outer join, we're going to get all the employees. So all these things in column last name are going to be populated, but the project number can be null because we did a left outer join. So that kept last name from failing, but project number can fail. Now we're coming to a feature that I really like, the using keyword. Okay. You may have noticed that in most of the joins we've done so far, when we use the join keyword, okay, and then we use we had an on condition. For the most part, the names of the columns were the same, and that's going to be the usual case. We're using these columns to set up relationships. Okay, they're foreign keys, and a good practice is, whenever possible, to use the same name for the column. So, can't we capitalize that? Can't we capitalize on that in the coding? Yeah, we can. So instead of having to say here, vendors join invoices on vendors.vendor ID equal invoices.vendor ID. If the name of the two columns are the same, we can just say using And now here's the difficult part to remember. You have to put the name of the column in parens, vendor ID. Okay, now I think that that's really succinct, really elegant. I like it a lot. So this is something that I use a lot because I think it reads well. Okay, is it any more efficient? No, I don't think it is. Is it any more right? No, I don't think it's any more right. I just like it. So it's a matter of style. Here's a case where we're using the using keywords where we're trying to join three tables. So we're joining employee departments to employees to projects. And of course, we need two links. So we've got two join keywords, and each one has a using. The first one on department number and the second one on employee ID. And you can see that we've put those into parentheses. Okay? Kind of a syntax shortcut that I like a lot. Now, there is something called a natural join. Now, I'm going to explain it, and you're going to find it appealing. And then I'm going to talk you out of using it. Okay? So instead of saying what fields we're joining on, instead of saying using this and this and this, or on this equal that, that equal that, that equal that. Instead of doing that, we can say we want to do a natural join, in which case it's going to join based upon matching column names. So if you set up your column names the right way, that would be really cool. So here's what we did here. We said select invoice number vendor name from vendors, natural join invoices, okay? And it turns out, I think that's what we just did, and that's on vendor ID, right? So that works fine. The only problem is, what if somebody down the road adds another column to one of those two tables that all of a sudden it matches to? Then your testing is going to be thrown all amok, okay? So I don't like things that can change if you add columns, okay? If you subtract columns, you're bound to break some of your queries. But if you simply add a column in one of the tables, this could actually change the behavior of the query, and that might not be what you want. So do I want you to understand what the natural keyword does? Yeah. Do I want it to be your favorite practice? Well, probably no. And here's a case where they used it to that joins three tables. So it's joining departments to employees to projects, and it's using a natural join. Okay, it's using a natural join and a using join. Okay, so you don't have to use all natural, all using. Every join can be implemented using any of those three approaches. Okay, cross joins. So what's a cross join? A cross join is where you get a row in the answer set for in the answer set for every row in table A times the number of rows in table B. Okay, so let's say we had 5 rows in table A and 6 rows in table B. If we did a cross join, we would get 30 rows in the answers in the results set. Now there are times when you want like every permutation, like every combination of anything in table A and anything in table B. Uh, let's say, we've got this is a menu at a restaurant where you can order two things. Okay, and you've got one from table A, one from table B. Okay, well, what kind of combinations can you have? Well, I guess you could have, and if they had five in one table and five in the other, how many possible combinations are there? Well, there are 30. Okay, now when you do that, this 5 times 30, and you get all those rows in the answer set, we call that the Cartesian product, and that has to do with the mathematics behind relational databases. Okay, now there are times when you want this. Okay, and if you want this, you can just simply say table 1 cross join table 2, and you'll get the combination of those two. Okay. It's possible to do this implicitly. This is why I don't like the implicit join syntax. Because if you forget to code a where in a join, and you're using the implicit syntax, you will get a cross join. And you will get the Cartesian product, which means you will get the number of rows in table A times the number of rows in table B. Well, in this case, it was probably 9 times 5. You got 45. Okay, that's not bad. And you look at it and you go, oh, that's not what I want. Okay, that's all right. Let's say we've got 100 rows in table A and 100 rows in table B. I think that's going to give you 10,000 rows. Well, that'll take a while to come back. Okay, that'll keep the server working for a while. Let's say you've got 50,000 rows in table A and 1,000 rows in table B. You're going to be there for the rest of your life. Okay, so these cross joins, if you want to do them, if you're doing them intentionally, it's a great thing to do. Okay, it's a really easy way to see all the permutations between two tables. But historically, back when we were doing joins with the implicit syntax, we would accidentally leave out the where clause like we have here on slide number 29, and we would get the Cartesian product, and we would be there for the rest of our lives just waiting for the server to get finished trying to come up with the answer set. So that led to the explicit join syntax more than anything else, because this was a common mistake. You just accidentally forget the where and you're gone. Whereas if you're using an explicit join, well, you can still accidentally get the Cartesian product, but it's harder to do. Okay? So that's why we want you using the explicit join syntax. Here are some terms to know. An outer join. Well, an outer join is a join where one of the two tables is allowed to fail to match. So you still put it in the answer set, even if there isn't a match on the other side. And this works really well for things that we expect not to be matched in some cases. Okay? A left outer join, it's the left table that doesn't have to match with the right. So if you don't find anything in the right for the left, you still get that row with the data in it from the left and nulls in it in the columns from the right. If you do a right outer join, well, the same thing. It's the right table that's non-failing. It's the right table that doesn't have to match the left one, and you'll still get rows from the right, and you'll get nulls in the fields that would have come from the left. Okay? There are, in terms of using outer joins, um, if in fact we've got good database integrity, there are a lot of applications where we're not expecting to have to use outer joins at all because we expect to set up these relationships with foreign keys, and we expect to implement constraints on the foreign keys where um, the database server isn't going to allow us to add um, a row in table A unless it's properly pointing to a row in table B. If that's going to happen, then we're not really going to have a lot of use for outer joins. We have a use for outer joins in really two kinds of circumstances. One is where we don't have good database integrity, and we have situations where we should have a relationship between all the rows in one table and all the rows in the other table, and it's just not there. So we want to do this kind of query just to go find the anomalies and clean up the data. And then the other one is where we have optional relationship. I talked about that a while ago, where we have maybe every customer, not every customer has their own salesperson, but some do. Okay, and the ones that do have have a foreign key that points to an employee. The ones that don't have a null there. Okay, that's a great case for using an outer join to list all the customers and the employee if they have their own salesperson. And if not, you're going to get null. Okay, that's part of the application design. That's why we have outer joins, and you're expecting that to work all the time. The next one's an equijoin. Those are the typical joins that we have where we're expecting the columns in the two tables to be equal. Okay? A natural join, we're expecting one or more columns to be equal, but we're too lazy to say explicitly what we think they are. I think that that's maybe not a good practice. A cross join, that's when we want to get a line, we want to get a row in the result set for the product of table A and table B. So if we have 9 in table A and 5 in table B, we're going to get 45 rows in the answer set. There are not a lot of situations where you want that, but when you want it, it's a really nice tool. Okay? You don't want to get it accidentally when you've got large tables. Okay? One of the nice things we can do, so when you get that entire cross-join multiplying answer set, that's called the Cartesian product. Okay? So again, if this is something that you want, I think you want to explicitly use the keyword and ask for a cross-join. You don't want to accidentally get it, especially with big tables, because you'll be waiting forever for your server to come back. And in the meantime, you'll be twiddling your thumbs. Now, the last thing that we cover is a union operator, which is pretty cool stuff. So far, all the questions that we've been posing with our selects are questions that can be answered with a single select. Okay? And selects are pretty capable. Okay? So there's a lot of things that can be answered by a single select. However, there are situations when we want to do more challenging things that the easiest way to do them is to do 2 selects and then union the results. Okay, so you've got essentially 2 queries. The answer to 2 queries when unioned together give you just what you want. So some of the rows are going to come from query 1, and some of the rows are going to come from query 2, and when you add those together, you have just the number of rows that you want. And would it have been easy to code just one select and get all the rows that you want? Well, for one reason or the other, not so easy as using this union operator. Okay, so it's kind of a big gun tool for a tricky set of circumstances, but you should be glad to have it when you need it. So how does it work? Okay, so we say we have one select statement, and it can be pretty complex like the ones that we've seen before. And then we can say union and then another select. We can do it again, and we can keep on doing it. Okay, so what this essentially does is it unions them all together. It becomes the sum of the rows from statement 1 and statement 2 and statement 3. And there are some options like all, but for the most part, what we're doing is we're getting a subset of the rows in the results set are coming from statement 1, a subset from statement 2, if there's a third or a fourth or a fifth from them too. And we are adding all those rows together and getting a combined answer set. Okay, now here are some of the restrictions. Each result set, so the results of each select must return the same number of columns. The corresponding columns in each result set must have compatible data types. And the column names in the final result set are taken from the first select clause. Okay, let's go explore that a bit. Okay, so here we've got two selects. Okay, and we are in the first one, we are selecting from active invoices. In the second one, we're selecting from paid invoices. Now, active invoices and paid invoices in this database or schema are two different tables. I would imagine they have the exact same definition, except that at some point, when invoices get paid, we take a row out of active invoices, we delete a row from active invoices, and we insert a row into paid invoices. Okay, so to really get a comprehensive answer, we need to look at two tables. Okay, and so interestingly here, the first column that we select is literal. So if it's coming from the first select, the first column says active. If it's coming from the second, the first column says paid. That's how we're going to get the difference. So look down in the results set, you see that some of the rows say active and some say paid. Now that's how we know what table they came from. Okay? And then we've got, in both cases, we call that source. Then we have invoice number, invoice date, invoice total. So all the fields are pretty much the same. The trick here is that they're coming from two different tables, and we're using this literal active or literal paid in column 1 that we're calling the source as a way to be able to identify the rows. Okay, so then we union them. They're combined. All those rows are combined to make the result set, and then we order them by invoice total, so that's how they become intermixed. Again, without an order by, we don't have a reliable order for the rows. So that's why we have one active at the top, then a whole bunch of paid, then two actives at the bottom, and then of course there are more rows that we can't see. So this is a classic kind of trick you can use to take like tables and combine their data using the union keyword. Here's a union that combines results from a single table. Okay. So how do we do that? Well, we're going to have a where that's going to select things that are active and a where that's going to select things that are paid. Okay, so let's look at the first select. It's still creating that source column with the word active, but it's only going to take the ones where the invoice total minus the payment minus the credit is greater than 0. So something is still owed on this. Okay, so then it's going to select that row and include that value active. And then in the second one, it's going to give the value paid, and then that same calculation has to be less than or equal to 0. Okay, so we get the same kind of thing from the same table. So pretty tricky, huh? It might not have been this something you would have thought of on your own, but this is a common way to do things. A union that combines result sets from the same two tables. Okay, so select invoice number, join vendors, invoices, join vendors, blah, 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 blah. So we've got some of these are going to have, the first group are going to have this 33% payment as the payment type, and then the second group are going to have this. So this is how we can get value from having two different selects, and then of course we have another union here. We've got paid in full, and we do invoice number, payment type. Here we've got a whole bunch of things there. Okay, so it's not something that I would have thought of on my own. It's something that it's a practice that you get used to over time. You sort of scratching your head and you go, oh, how can I get that into one query? And they go, well, maybe I can't. Maybe I can have two queries and union them. Okay. I just want to point out the restrictions again. Okay. Each result set, so each of the selects must return the same number of columns. The corresponding columns in each result set must have compatible data types. And the column names in the final result set are going to be taken from the column names in the first select clause. Okay? So you're going to have to live with that. Now the very last thing that we show you in the chapter is a union that simulates a full outer join. Well, what's a full outer join? Well, this is the thing that doesn't have a direct way to code in MySQL. You'll remember that a left outer join gives you all the rows in the table on the left, even if they're not matched on the right. Right outer join gives you all the rows from the table on the right, even if they're not matched on the left. A full outer join gives you both. Okay. This is not a common use case, but you could use a union to get, well, what you do is you union a left join with a right join, and you get them both. Okay. Now, again, I'm not sure what your use case is. Okay. One of the reasons that we don't have an easy way to code this is that it's not a common use case. Terms to no union. That's where we're going to combine the rows that come from two queries where we've used the union operator in between them. And a full outer join is a join where we get essentially all the rows regardless of whether they matched or not on either side. And again, it's very hard for me to give you a use case where I would want to do that. I could see where I might want to create some kind of a listing where I would go and analyze my database integrity or something like that. But commonly, if I've got control over relational database integrity, I'm probably not going to be doing something like a full outer join. Certainly, it's not something that I come up against in my applications. Well, really ever. I don't think I've ever done a full outer join. I'm sure that you'll find one because now I've told you that you won't. Well, that is it for Chapter 4. This is the main event. This combining the table, the data from more than one tables, because when you are using a well-designed, normalized relational database, this is going to be very common. I mean, this is going to be the typical use case. So it's something you're going to get very good at, right? I'm going to say bye until next time. Bye-bye.